Hi everybody, so today we're going to look at answering a question about an induced EMF in a coil. So with these questions, it's important to look at two different positions of the coil. Imagine this is our coil here. So what we're going to do is we're just going to insert it sideways. Imagine this is a side-on view of our coil. And then we're also going to look at when it's rotated 90 degrees, what that will look like. So if it's rotated 90 degrees, our coil will look like that. Now, the formula that we use to calculate the induced EMF is the number of coils times the change in flux divided by the change in time. We also have a formula we're going to use here, which is the formula for magnetic flux, which is magnetic flux is equal to magnetic flux density times the cross-sectional area. So we're just going to look at this formula here for a second first. What's important to realize is that the magnetic flux depends on the cross-sectional area that's exposed to the magnetic field. So on this one here, we have a very large area exposed to the magnetic field, and lots of magnetic field lines passing through it. In this here, where it's rotated so that it's parallel to the direction of the magnetic field, we see actually no magnetic field lines pass through it. So the area here is going to be 0, and that means magnetic flux for this one here is going to be 0. So our first step then is going to be to look at the magnetic flux here. We know that the change in magnetic flux then will be the difference between this and 0. And then we're going to fill in the time it takes for it to go from here to here. So let's just look then at this first one here. Shown here on the left. Now, question 16 part A asks us what is the change in flux as it moves through the first two positions. So if it goes from this position where the magnetic flux is 1.275 × 10 to the minus 2 Webers to this position where we've already said because the area is 0, the magnetic flux is 0 as well. Then the total change must be 1.275 × 10 to the minus 2 Webers. So now looking at part B, it asks us what the average induced EMF is. So what we're going to do is use this formula here, again E being our induced EMF, and we're lucky because we only have one turn of the coil. We just said that we know the change in flux is 1.275 × 10 to the minus 2 Webers. So we just need to figure out what the amount of time is as it goes from here to here. So let's have a look at that now. So now we're really just looking at changing some units around, and they're testing our understanding of that. So we're told there's 15 revolutions of this coil per second. Now, in order to go from our first position to our second position, or to rotate 90 degrees, that's a quarter of a revolution. So that means it's going to be 15 times 4, or 60 quarter revolutions per second. I'm just going to put down ReVQ for quarter revolutions. Now, if there's 60 quarter revolutions per second, then if we divide a second into 60 parts, that will be the amount of time between each of those quarter revolutions, or the amount of time it takes for our coil to go from this position to this position. Again, a quarter turn. So if we divide 1 by 60, we get 1.667 by 10 to the minus 2 seconds. Again, that's the time it takes for a quarter turn to go from an upright position to a 90 degrees rotated position. Now we can just fill all the information we've gathered so far into our formula for induced EMF. So our induced EMF is equal to N, the number of coils, times the change in magnetic flux, divided by the change in time taken for that magnetic flux to change. Filling that in, we know the number of turns in the coil is 1. We know that the magnetic flux change is 1.275 × 10 to the minus 2. And we know the change in time is 1.667 times 10 to the minus 2. If we calculate all of that out, we will get an induced EMF of 0.765 volts. We are told that the area of that coil is 25 centimeters squared, and we're told that the magnetic flux density is 5.1 teslas. Now, of course, we should be spotting at this point that this is not the standard unit for area, so we need to change that into meters squared first. So we'll have a look at how we do that now. Remember, I think a very good way of doing this is to just draw out a meter squared, but break it up into whatever unit you're trying to convert to. So a meter squared would be 100 centimeters by 100 centimeters. If we multiply them, that would give us a total area of 10,000 centimeters squared, which is the same as our 1 meter by 1 meter, or 1 meter squared. So 1 meter squared is equal to 10,000 centimeters squared. If we wanted to change 25 centimeters squared into meter squared, well, we have to either multiply or divide that by 10,000. We know the number is probably going to get smaller if we're going from centimeter squared to meter squared, so we're going to divide it. So 25 divided by 10,000, that's going to give us 2.5 times 10 to the minus 3 meters squared. At this point now, we have our area in meters squared, we have our magnetic flux density in teslas, so we're ready to go ahead with the formula, which is our magnetic flux is equal to our magnetic flux density times the area. Again, make sure you always write out the formula, but then it'll just be 5.1 times 2.5 times 10 to the minus 3. If you multiply that out in your calculator, you will get 1.275 times 10 to the minus 2 Webers. Now remember that this is just for our first